Welcome to the Platform Engineering Playbook Daily News Podcast. Today's news and a deep dive to help you stay ahead in platform engineering. Today we're breaking down the security ops specialty, one of the most valuable skills platform engineers can develop in 2026. But first, here are today's top stories in platform engineering. First up, Kubernetes SIGs has released Agent Sandbox, an open-source controller for securely running AI-generated code on Kubernetes clusters. It uses gvisor to isolate untrusted code from the underlying node, with optional Kata container support for even stronger isolation. This directly addresses one of the biggest challenges with AI agents. How do you let LLMs execute code in production without blowing up your cluster?
That's huge. The security implications of AI agents running arbitrary code have been a major blocker for enterprise adoption. Having a Kubernetes native solution with proper sandboxing is exactly what platform teams need.
Second, Backstage just published their 2025 year in review, and the numbers are remarkable. 3.4 thousand adopters globally, 89% market share in the IDP space, according to a DX survey, and over 250 open-source plugins. The new front-end system is now adoption-ready, and they've launched an actions registry with MCP server support for AI integration.
89% market share is wild. Backstage has essentially become the de facto standard for internal developer portals.
And third, there's a great discussion on Reddit about handling API key and certificate expiries without spreadsheets. The thread highlights how many organizations still track critical credentials manually and the postmortems that follow when something expires unexpectedly.
That's actually a perfect segue into today's topic. Security ops and credential lifecycle are core security ops skills.
That's the news. And now, today's main topic, security ops for platform engineers. Jordan, in our recent episode on platform engineering salaries and skills for 2026, we identified security ops as one of the top specialty areas. Why is this becoming so critical?
Two reasons. First, platform teams are increasingly responsible for the security posture of everything they provision. When you build a self-service platform, you're not just giving developers compute resources, you're establishing security boundaries, enforcing compliance, and managing the attack surface. Second, the security landscape has changed. Supply chain attacks, runtime threats, and identity sprawl have made perimeter security obsolete. The platform is the new perimeter.
Let's break this down. What are the core domains within security ops that platform engineers should focus on?
I'd group it into 5 areas: supply chain security, secrets management, runtime security, identity and access, and compliance as code. Each has its own tooling, patterns, and career depth.
Start with supply chain security. This has been in the headlines constantly, especially after SolarWinds and Log4Shell.
Supply chain security is about ensuring that everything in your software delivery pipeline, from source code to container images to third-party dependencies, hasn't been tampered with and comes from trusted sources. The key tools here are SigStore for signing and verification, Trivy and Gripe for vulnerability scanning, SLSA for build provenance, and software bill of materials tools like SIFT.
Walk me through how SigStore actually works under the hood. I think a lot of platform engineers know they should use it, but don't fully understand the architecture.
SigStore has 3 main components. First, cosign handles container image signing using keyless signatures tied to your identity provider. You authenticate with your corporate identity, and SigStore issues a short-lived certificate. Second is Record, a transparency log that records every signature. Think of it like certificate transparency for software artifacts. Anyone can verify that a signature was recorded at a specific time. Third is Fulcio, the certificate authority that issues those short-lived certificates based on OIDC identity tokens.
So there's no long-lived private key to manage or rotate.
Exactly. That's the keyless part. Your identity provider is the root of trust. When you sign an image, you authenticate with GitHub, Google, or your corporate OIDC provider. Fulcio verifies your identity and issues a certificate that's only valid for 10 minutes. The signature gets recorded in Record, and then the certificate expires. Verification happens by checking Record, not by managing public keys.
And how does this integrate with Kubernetes admission control?
That's where SigStore Policy Controller comes in. It's an admission webhook that validates signatures before allowing pods to run. You define policies that say which identities or key authorities are trusted. For example, you can require that all production images must be signed by your internal CI system. If an image isn't signed or signed by an untrusted identity, the deployment is rejected automatically.
That's the golden path approach applied to security.
Exactly. And the tooling has matured dramatically. SigStore's cosign is now widely adopted for container signing. Trivy runs in under a second for most scans. You can implement real supply chain security without slowing down deployments.
Let's talk secrets management. This seems like table stakes, but the Reddit thread we mentioned suggests many orgs are still struggling.
Secrets management is deceptively complex. The basic problem, storing credentials securely, was solved years ago with tools like HashiCorp Vault or AWS Secrets Manager. But the hard parts are lifecycle management, rotation, and access auditing. How do you rotate a database password without downtime? How do you know which service accessed which secret and when? How do you revoke access when someone leaves?
Let's go deeper on Vault specifically. What's the architecture that platform engineers should implement?
Vault has a concept called secret engines that generate credentials dynamically. For databases, instead of storing a static password, Vault connects to your database with admin credentials and creates new database users on demand. When a service needs database access, it authenticates to Vault, and Vault creates a temporary database credential and returns it. The entire chain is tied to the pod's identity. No shared secrets, no manual rotation, complete audit trail.
Walk me through the authentication flow.
For Kubernetes workloads, you typically use the Kubernetes auth method. Vault validates the pod's service account token against the Kubernetes API. If the token is valid and the service account is authorized, Vault issues a client token. The client uses that token to request secrets from the database engine. Vault creates a temporary database credential and returns it. The entire chain is tied to the pod's identity. No shared secrets, no manual rotation, complete audit trail.
What's the platform engineering approach here?
You build secrets as a platform capability. Developers request credentials through an API or self-service portal. The platform provisions short-lived, auto-rotating secrets. Access is tied to workload identity rather than long-lived service accounts, and everything is logged for compliance.
You mentioned workload identity. That bridges into the identity and access domain.
Right. Spiffy and Spire are the key technologies here. Spiffy is a standard for workload identity, giving every service a cryptographic identity that's independent of the underlying infrastructure. Spire is the reference implementation. Together, they enable zero-trust networking, where services authenticate to each other based on verify identity, not network location.
How does Spiffy identity actually work at the infrastructure level?
Spiffy defines a format called SVID, Spiffy Verifiable Identity Document. It's essentially an X509 certificate where the SAN field contains a Spiffy ID, which looks like a URI, Spiffy:// trust domain/workload identifier. Spire runs agents on each node that attest workload identity based on multiple factors: the Kubernetes service account, the pod's namespace, labels, even the container image hash. Once attested, the workload receives an SVID that's automatically rotated, typically every hour.
This is a significant mindset shift from traditional security models.
It is. In traditional security, you trust the network. If a request comes from inside the firewall, it's probably legitimate. In zero trust, you trust nothing. Every request is authenticated and authorized, regardless of where it originates. Platform engineers implementing Spiffy and Spire are building the infrastructure layer that makes zero trust possible.
Let's move to runtime security. What does this encompass?
Runtime security is about detecting and responding to threats in running systems. The key technology is eBPF, Extended Berkeley Packet Filter, which lets you instrument the kernel without modifying it. Falco is the most popular tool, created by Sysdig and now a CNCF project. It watches system calls and container behavior for anomalies.
Let's go deeper on eBPF. What makes it so powerful for security?
eBPF lets you run sandboxed programs inside the Linux kernel. These programs can hook into kernel events, system calls, network packets, file operations, and execute custom logic in response. The key innovation is the verifier. Before any eBPF program runs, the kernel analyzes it to guarantee it terminates, doesn't access invalid memory, and can't crash the system. This makes it safe to run custom code in kernel space, which was historically impossible without writing kernel modules.
And how does Falco use eBPF for threat detection?
Falco attaches eBPF probes to system calls. Every time a process opens a file, makes a network connection, or executes a command, Falco captures that event with full context: the process hierarchy, container ID, Kubernetes metadata, everything. Then it evaluates rules against that stream. Rules can detect things like a shell was spawned in a container that normally doesn't run shells, or a process is reading etc shadow, or a container is making network connections to unexpected destinations.
What kind of anomalies should platform engineers watch for?
A container suddenly opening a shell, a process making unexpected network connections, files being modified in read-only directories, credential files being accessed. Falco can detect these in real time and trigger alerts or even automatic responses.
Can you give a concrete example of a Falco rule?
Sure, here's a common pattern. Detecting when a shell is spawned in a container, the rule watches for exec v system calls where the process name is bash, sh, or zh, and the container ID is not host. You can add exceptions for containers that legitimately need shells, like debug sidecars. When the rule triggers, Falco can send alerts to Slack, PagerDuty, or trigger a Kubernetes response like killing the pod.
This connects to the agent sandbox we mentioned in the news. Running untrusted code safely requires this kind of runtime monitoring.
Absolutely. And as AI agents become more prevalent, runtime security becomes even more critical. You need defense in depth, sandboxing at the container level with gvisor, SecComp profiles filtering which system calls are allowed, and runtime monitoring with Falco to detect anything that slips through.
The fifth domain you mentioned was compliance as code. What does this mean?
Compliance as code means expressing security and regulatory requirements as executable policies. Instead of a PDF that says all containers must run as non-root, you write an OPA policy that enforces it automatically. Open Policy Agent, or OPA, with Gatekeeper for Kubernetes is the standard approach.
Walk me through how OPA and Gatekeeper work together.
Gatekeeper is an admission controller that delegates policy decisions to OPA. When a Kubernetes resource is created or updated, Gatekeeper sends the request to OPA with the full object and context. OPA evaluates policies written in Rego, a declarative query language. If the policy returns a violation, Gatekeeper rejects the request with the violation message. Policies are stored as Kubernetes custom resources, so they're version controlled and deployed like any other configuration.
How sophisticated can these policies get?
Extremely sophisticated. You can enforce network segmentation, require specific security contexts, validate resource configurations, ensure encryption at rest, and audit access patterns, all through declarative policies that are version controlled and tested like any other code. This is where platform engineering and security engineering truly converge.
Let's talk about the career path. How does a platform engineer develop these security skills?
I'd suggest a progression. Start with supply chain security. It's the most immediately applicable. Learn Trivy for scanning, implement SIG-Store signing in your CI pipelines, understand SBOMs. This gives you quick wins and visible impact.
Then what?
Move to policy as code with OPA. This builds on your existing Kubernetes knowledge and has broad applicability. Write policies for your admission controllers. Learn Rego, OPA's policy language. Once you're comfortable with policy enforcement, you have the foundation for everything else.
And the more advanced areas.
Secrets management with Vault comes next. Understanding PKI, certificate rotation, dynamic secrets. Then SPIFFE and Spire for workload identity. And finally, runtime security with Falco and eBPF. That last one is deep. eBPF is essentially a new programming paradigm for observability and security.
What certifications or formal training would you recommend?
The Certified Kubernetes Security Specialist, CKS, is valuable because it covers many of these areas within a Kubernetes context. HashiCorp has certifications for Vault, and there are SANS courses for cloud security, though they're expensive. But honestly, hands-on experience matters most. Build a lab, implement these tools, break things, and fix them.
Are there teams that combine platform engineering and security effectively that we can learn from?
Several companies have shared their approaches. Netflix's security team has published extensively about their platform security practices. Spotify has talked about their golden path approach to security guardrails. And the Kubernetes Security Special Interest Group produces excellent documentation and tooling.
What about organizational structure? Should security ops be part of the platform team or separate?
There's no universal answer, but the trend is toward embedded security. Having a security specialist within the platform team or platform engineers with deep security expertise is more effective than a separate security team that reviews after the fact. Shift-left security requires security to be part of platform development, not a gate at the end.
Let's get tactical. If someone listening wants to start building security ops skills this week, what should they do?
3 things. First, add Trivy scanning to one of your CI pipelines. It takes maybe an hour and immediately surfaces vulnerabilities you didn't know about. Second, write one OPA policy for your Kubernetes clusters, something simple like requiring resource limits or disallowing privileged containers. Third, deploy Falco in audit mode on a non-production cluster and observe what it detects. These 3 actions touch supply chain security, policy as code, and runtime security.
What's the salary impact? We talked about specialties commanding premiums.
Security-focused platform engineers typically command 10 to 20% higher compensation than generalists. The demand far exceeds supply, and the combination is particularly valuable. Many security engineers don't have deep platform or infrastructure experience, and many platform engineers don't have security depth. Bridging that gap is career gold.
Any pitfalls to avoid when developing these skills?
Don't try to learn everything at once. Security is vast, and you can spend years going deep on any one area. Pick a domain, build real expertise, then expand. Also, don't treat security as something separate from your platform work. Integrate it into everything you build. The best security is invisible. Guardrails that protect without impeding.
Final thoughts on where this specialty is heading?
AI is going to transform security ops just like it's transforming everything else. Automated threat detection, policy generation from natural language requirements, anomaly detection at scale, these are all emerging capabilities. The agent sandbox we mentioned is just the beginning. Platform engineers who understand both the AI and security domains will be extraordinarily valuable.
That's it for this episode of the Platform Engineering Playbook Daily Podcast.
We covered the 5 core security ops domains: supply chain security with SigStore and Trivy, secrets management with Vault and dynamic credentials, identity and access with Spiffy and Spire, runtime security with eBPF and Falco, and compliance as code with OPA and Gatekeeper.
If you want to go deeper on any of these topics, we have full show notes with links to every tool and concept we mentioned at platform-engineering-playbook.com.
And if this episode helped clarify where platform security is heading, subscribing wherever you listen helps us know to keep making content like this.
The platform is the new perimeter. The time to build security ops skills is now.